Welcome to the AV Experience from your host, Ryan Charpentier of Ascend Audio Video, joined by Ben Goff of Cinema Bureau, and this week by Adam Keplinger of Casaplex. And we are going to be talking about something that many people don't talk about or avoid altogether or don't even think about, gain structure. And this is something, and I'm going to throw this out there, that Adam knows far more than most. So I'm actually excited to learn something in this along with all of you. And we're not going to sit on this introduction very long because I think this topic's got some gusto. So we're just going to jump straight into it. So Adam, I'm going to turn this directly over to you. Before you jump into this, if you want to tell people a little bit about who you are and then just segue right into the topic, we can get moving.
Can I do it for you, Adam? I think it's more fun. So Adam's credentials are impugnable here. We've taught this content together. So this is content that we've taught to, I guess, 100 or more professional integrators at Expos. Adam is currently the vice chair of the whole of CEDIA standards. He is a CEDIA awards judge. He's a proper actual engineer with proper actual engineering qualifications. So, you know, when Adam speaks on a topic like this, we just listen.
I would agree with that. I don't know Adam, or haven't known Adam for very long. But since and during that time, I would agree with everything that you just said. So Adam, just a little bit about yourself, and then we'll jump straight into this. Maybe.
We may have, oh, are you there, Adam?
Side. Okay. All right. It's just been my thing since I was 15, and I never thought I'd be able to do such. And in the residential AV world, people don't seem to know that math exists, and it's still very real. So I guess we can just go ahead and start into this. So
yeah,
I may have Ben talk about the first couple slides.
As you bring it up, Adam, when was your full transition really from being commercial AV to residential? When did you move to residential full time?
So I moved to residential in around 20. I realized that the AV world and the commercial world, all they wanted were conference rooms, and that was pretty boring to me. And all of the really cool projects that I used to do with defense contractors that look like big NASA walls, those just kind of down my like to do. So I just decided that I was going to take a leap. Didn't even have a job at the time, but I quit my other job, figured out what I wanted to do, found a great company that I like working for with great people, and started my ascent of the Dunning-Kruger mountain of stupid and not knowing what I didn't know. I had actually built the room that I'm sitting in about 10 years ago, before RP22 existed and before all these, the ability to really predict what you were going to do was a thing. And my camera just went out and back in.
I would just, Adam, I would just leave your camera off because it's choppy.
All right, I can totally do that. That may actually
perfect. I think that'll actually help the audio.
All right, well then why did I worry about all my lighting and getting everything working? But perfectly fine. I'll do whatever's better. You don't need to see my face. But at any rate, so you know, I built this room 10 years ago. I didn't really know what I didn't know. When we first designed it, Dolby Atmos didn't exist. So 7 speakers was the most I could do. And yeah, Peter's telling me my connection is very shonky. So sorry, Peter.
No, you're good.
But so it's good now that my video's off?
It's better, yes.
We can hear you much better now, yeah.
Okay. So when I built this room, I really didn't know enough. And I think that in 2020 and 2021 is when I kind of started getting back into the field. And I went to an RP22 presentation from Ben and Peter in this first CEDIA after I started in the Resi world. And that presentation completely blew my mind. And Peter kept asking me questions about very detailed things. And I'm like, I can't answer this. I need my computer. I need all my resources. I need to look at 15 spec sheets, and I need to make a really big spreadsheet. And so I spent about a year making a massive spreadsheet on how to figure out how to calculate most of the things that are in RP22 and predict them so that I could be a better designer. And I like the idea that I could do it all before the walls were built, before the speakers were fixed in position, when it was in the design part, not in the, oh, it's really expensive now to move a speaker 8 inches because I missed a parameter. So that's kind of my ascent into the CEDIA world. And I've definitely have glammed on to some really lovely people, and they become some of my closest friends, and it's just been great. So do you want to go ahead and put the presentation up, and we'll go ahead and start talking about it?
I can certainly do that. There we go.
All right, so this is going to get real nerdy, and I apologize for that, but I don't apologize for that. This is kind of a nerdy topic. So I'm going to try to start from the beginning about how this all works. So we're talking about gain stage, and when we're talking about gain stage, we need to not be talking about volts and amps and watts, because that's not how we really perceive things. We really need to be talking about things in decibels. And so I wanted to kind of start with this. Most people on this call, because this is not, this is really an inside baseball kind of call. There aren't a lot of complete new audio people to this. But a decibel is a relative unit of measurement. And it's a ratio between two values on a logarithmic scale. Logarithms are really mess with your brain because it's just it's a different scale. And Ben could explain this a little more eloquently. Mm-hmm. But when you're doubling the amplifier power, it's 3 dB. 10 times the amplifier power is 10 dB. There's not that difference isn't linear like it is in the rest of our world, how we normally think of things. And one of the other weird things is that a 10 dB increase in sound appears to us as roughly twice as loud, whereas a 6 dB decrease seems half as loud. And that's super weird. And it's because people just aren't microphones. And so it's just an unusual thing. Ben, do you want to say anything else on dB?
No, I mean, that scale you're showing there is specifically dB of sound pressure level. So dBs can be applied to anything. So I forget the slides we're going to show, but in a minute, we are probably going to look at a dB scale of volts, which is still a logarithmic scale, but this particular you're showing now is sound pressure level. But dB is not limited to that, right? So we can use the dB scale for other things than just how loud sound is.
Exactly. So the question of how much gain do I need? We're talking about trying to get our preamp, amplifier, speakers, and the audio that coming through the room to be enough. And how much gain do I need? The answer is enough, but that's not very helpful. So ideally, we're trying to drive an amplifier to clipping and not much more. So the picture on this slide shows power coming out of an amplifier in watts. And you'll notice that the scale on the bottom it's a logarithmic scale. So it has 1, 10, and 100, and the little tick marks are not evenly divided. So each tick mark essentially is a little bit further away than the last one. That's just what the logarithmic scale looks like. And 10 is about the same number of 10 watts and 100 watts, and between 100 watts and 1,000 watts, it moves in a way that 1,000 watts is not as loud as we would think it would be, and 10,000 watts is not that much louder. It really messes with our brain. So in order to figure this out, we need to know the output power at clipping of the amplifier. We need to understand the preamp voltage output, what it can do, the speaker impedance, and then once we know all those things, we can figure out how much amp gain is required to make it so that the speakers are getting, that the amplifier, I'm sorry, is getting the right amount of input to be able to be driven to clipping, but not much more. This next slide, this is a slide with of some meters that I took a screenshot of. This is a Trinov slide here. So some preamps or DACs are directly connected to an amplifier. They're the gain knob that you turn the volume up. So is not a large scale integrated circuit. Literally, the output of that goes essentially straight to the amplifier. And because of that, they have a fixed noise floor because the DAC always is producing some noise, and there's nothing to attenuate it between it and the amplifier. And they will have a discrete clipping point. And you basically have to assume that all the sound that we're hearing lives between that noise floor and the clipping point. So if you have too much gain in your amplifier, then the system's noise floor is going to be unnecessarily high because you're not actually using all of the digital bits in the DAC. There are a whole bunch of zeros at the beginning that you're not even utilizing, but the noise floor of the DAC is still where it is. If you have too little amp gain, then the DACs are going to clip and run into clipping. So on the picture on the left, this is actually a screenshot of the Trinov playing Ready Player One. And as everybody knows, it's a really hot mix. So I put the meters to hold so that they would record what was going on in the mix. And every single one of them, except for one of the surrounds, is maxed out. And what you'll notice on the right, those are the output meters. There are only 4 of them just because I didn't have enough room on the screen to capture it. This is when my system was playing pretty loud, but still about 5 decibels below reference level. And you'll see on the right that my meters are showing around 6 decibels below maximum digital output. And so I basically had about 6 dB of headroom in the system, which is about right. And it's really what I wanted to do.
And what you're talking about specifically here is the green bars on the right are not maxing out to 0. Is that correct?
That's correct. And had I turned it up to quote unquote reference level, they would be very close to maxing out because the volume but had I turned it down to 30 dBs below reference level, those meters would be way further down. And
what's the danger of maxing out?
It's digital clipping sounds terrible. It sounds really harsh and abrupt, and you never want your DACs to be digitally clipping. So you basically have to manage your gain structure so that your DACs do not clip. But also you want to use all the bits you have. In my mind, there's no point in having having the preamp be able to essentially put enough voltage out so that your room could play 160 dBs. You're not going to be playing that loud. Not even Ryan will play that loud. So you're wasting your noise.
I guess that's an interesting thing with the Trinov generally, and we'll look at some numbers in a minute. But the Trinov output side, so its preamp output is going to be a higher voltage than almost everything else we use in the consumer space. So in many cases, if you're using a Trinov with other amps, you will have that capability to overdrive your amps. And it's something that when we start to look at some numbers, I think there'll be a lot of people who haven't realized or don't understand why that is yet. Is Adam still there?
Yeah, I'm still here. And one thing that was interesting is I actually had this. Am I back now?
Yep,
you're back now.
I've had an interesting conversation. It took me a while to convince some of the folks at Trinov that an analog XLR pad, a 10 dB pad, would actually be helpful in a lot of systems. And because their perspective was, well, if you use our amplifiers, you don't need it. I'm like, you're right, but if you're not using your amplifiers, you've got to kind of simulate what you guys did with the gain structure of your amplifier to make it optimized. And they're like, oh yeah, that makes sense. So next thing we want to talk about is how much output voltage does a preamp have? So AVRs tend to have consumer level outputs, and they're much lower voltage capabilities than some of the pro style preamps designed. Am I back?
Yep, you're right. You're good.
All right, so they have a lower output than some of the pro style amplifiers. And the reason that pro amps use a higher voltage is specifically so they can get a better noise floor. And that's just something that that in the commercial audio world, everything is higher voltage. The reason that AVRs are lower voltage is because it's less expensive, and it was the standard from forever ago. But higher voltage outputs generally are better, but you have to still make sure that everything matches up. Let's see. I think that was all I wanted to say on the slide.
Yeah, but if you just go back one page, that's got there's a really interesting thing there that it said in that data that the Trinov Altitude 16 has its lowest signal to noise ratio when it's outputting between 3 and 6 volts. Now, a lot of consumer amplifiers would max out with an input of about 1.4 volts. So at that point, you're not using the altitude in its best range if you matched it with one of those amplifiers.
Yes, and how I like to say it is, if you think of all the digital ones and zeros, you have a lot of zeros at the beginning. So all of your information is shoved down to the end, and that's not the best circumstance for that preamp. And most preamps are not digital volume controls, and their noise floor actually changes as you raise and lower the actual volume knob on the front of the unit. So they're just two different things. And when you have a digital volume control, such as Trinov and Storm, and there are probably others, you just have to be very careful of how you do your gain stage. All right, so the next question is, how much gain does an amplifier have? So we need to consider the preamp and the amplifier to be a pair. They don't live in isolation of each other. And 12 dB to 32 dB is common. I think Trinovs are 18.
That sounds right.
And most consumer amps are probably in the 28 range. There's about a 10 dB difference. Level output and professional level output, balanced output that you would normally get in a professional product. And the other question is amplifier gain adjustable? So I personally have different amps for my LCRs that I do for my surrounds. And because I was have a less expensive amp, and it's my left, center, right amps are benchmark HB2 amps in bridge monoblock mode, and actually to hit exact right thing that I need to. On my surround amps, I have ATI multi-channel amp. Those have fixed input 28 dB, and that input gain does not match Trinov altitude. If I were to just connect them, I would output that the preamp is capable of, where its noise floor is the best, and where I'm getting the digital zeros to not have 100 leading zeros. That wouldn't be optimal. So I essentially threw in 10 dB pads. They're little XLR in and out connectors that are just resistors that reduce the level of the Trinov preamp output so that it matches the input on the ATI. And I then get a good noise floor, and I'm using all the digital bits, and it works out quite well.
So,
All right.
so a pad, Adam, is a passive attenuating device. Is that correct?
Yes. I don't know. I think that is why they're called pads. I never contemplated that. Like it's also called an H pad, and the H is because of the way that they put resistors in a specific pattern, in a specific configuration, to make it essentially just drop the voltage.
Yeah.
And it essentially just it drops the voltage by 10 dB.
Is there any negative to using pads?
No, not really. There's the noise that they introduce. It's literally just resistors. The most high-end perfect way to adjust volume is a resistor. So essentially it is the highest end way to do it. Resistors do have their own amount of noise, but it's so far below the gain you get that it's very much worth doing. So my room that I'm sitting in right now that you can't see because I turned my camera off was designed from the start to be a theater space. So we made a lot of consideration for the acoustics and the layout with very intentional compromises because this is also a family room, kitchen, dining room, community space. It was done 10 years ago, and partly because of that, and partly because I just didn't have the knowledge, it is not what I would say is a fully engineered per CD RP22 space, because it didn't even exist 10 years ago when we designed it. I didn't have enough knowledge to target and predict important audio parameters in the design stage when I built it. So I didn't do the math initially, even though I do have an electrical engineering degree and completely capable of doing the math. When I upgraded this room 5 or 6 years ago, I had an Marantz AV processor and some not spectacular multi-channel amps. I wanted to improve the sound quality. I then had a more complete knowledge, and I decided I needed to do the math before I purchased anything new.
Adam, before you run through all these numbers, we've had a question from Steve. Let's answer it before we carry on, because I think it will make more sense as we move forward. So Steve has asked, how do you know how much amp gain you have and how much you're utilizing? So do you want to explain how you could move between the number of watts an amplifier has and how that relates to its gain?
So hopefully the easiest way to know is the manufacturer tells you. And actually, Ben, I may have you want to talk a second about RP1 and DVR.
Sure. So
because
I mean, I would say
that is really the answer.
Right. So the good manufacturers will give it, right? Sorry, we're cutting over each other. I would say, right, so some manufacturers give us this in gain, like Trinov and Storm, people like ATI, their tech sheets will have this, but otherwise we can go from watts. So when we've done our calculations of the sensitivity, we'll know that how loud the system plays when we put 2.83 volts in. If we're using 8 ohms, that comes out as 1 watt. So the data sheets really are based around 1 watt. It's 1 watt as long as it's 8 ohms. So as soon as you go to 2 watts on an amplifier, you've doubled the amount of output. So that would be 3 dB of gain, because every time we double, it's 3 dB. So 2 watts into 8 ohms, you would have 3 dB of gain. 4 watts into 8 ohms is now 6 dB of gain. And every time we double that wattage, there's 3 dB more gain. So from 250 to 500 is 3 dB, up to 1,000 is 3 dB. That's the same gain as at the start of this amplifier, going from 1 to 2 to 4. So when you're at the lower end, increases in gain are easily come by. At the high end of power, huge numbers start to occur.
Is he asking, though, what the actual start gain of an amplifier is? Like, how do you determine how much gain you're actually getting from the start?
How much gain that amplifier will give you is based on how many watts it can output. So a 500 watt amplifier has 3 dB more gain than a 250 watt amplifier. if they have the same input sensitivity.
Yeah, and it
I
has
think
to do with
that's
the
what he's
input
actually talking
sensitivity
about, though, is
versus
the
the
input
output level.
sensitivity.
Yeah, and
Yeah, the input sensitivity versus the output levels.
so we'll need to know how many volts you need to drive it to its maximum output against what it outputs. So that's where the Trinov difference occurs. So an amplitude 16 from Trinov, you drive it to about 6 volts input, and then it only adds 18 dB of gain. Or is it 16 dB of gain? 16, I think.
I think it's 16.
Whereas a storm, you drive it with a lot less voltage in, but then it adds a lot more to it. So it's the gain that each component adds is the ratio of what you put in to what it gives out.
Yep. I see one other
Carry on.
question
The next
from our
question.
friend Tom.
There you go.
Why use an analog pad and not reduce the gain in the preamp? So when you have an analog volume control, probably reducing the gain in the preamp will be successful, but it is you still might have a better signal noise ratio if you still maximize the voltage output on the preamp to the amplifier. And with a digital volume control, you're increasing the noise every time you turn the volume down and raising the essentially there's a volume control. Think of the amplifier as having its own volume control. If you turn the volume control on the preamp down, but you turn the gain, which is the volume control on the amplifier. If you can essentially turn the gain on the amplifier, which is the volume control on the amplifier down, you can either do that with dip switches if it has it. You could do it with the pad if it doesn't. To match the two, that's how you optimize the noise floor. Okay, so let me keep moving here. So the room I built has natural performance limitations from our RP22 based on the room layout and the just functional requirements of the family space, which I think is really common for people. In my room, being an exceptional hi-fi system to me was a higher priority than extremely high SPL capability. Even though I really still wanted to know what it would be with the new gear that I was going to get to make sure it hit some reasonable goals for movie playback levels. So I started with the speakers, the YG acoustics I have. I literally talked to the CEO of YG Acoustics and had them field test an actual Talus speaker before I purchased it to make sure that they would have the SPL capabilities with pink noise that would allow me to hit the RP22 goals that I was looking for. And I had them give me the number both full range and bandwidth limited to 80 hertz where my subs take over. So I would know roughly what level of SPL I could get in this room. And from that, I was able to essentially work backwards and make it all to make sure that I had enough amplifier power to make sure all of my gain stages were appropriate. I am building another completely new structure behind my house, and that theater is going to be designed to hit all RP22 level 4 targets from the start. And that is super intentional to do and very difficult to accomplish. And like Ben has previously said many times, you kind of have to bring money. There's no way to do that in an inexpensive way. So moving on to
spreadsheet
this
is outlining
spreadsheet, this small portion of this.
You got it, Adam. Never mind. You were going to it.
Yeah, so I built this spreadsheet as a tool to be able to optimize the noise floor and simultaneously hit a targeted reference level. So essentially, and all of that has to do with gain stage. And the gain stage also includes the sensitivity of your speaker and also how much distance between the speaker and the reference position in the room, because all of those things add up to the SPL level that you actually hear. So the spreadsheet has tables built inside it with multiple amplifiers where I put all the specifications and all the different technical things for the amplifiers, for the preamp or DAC, and for the speakers. So I can actually, in this spreadsheet, pull down the things at the top for each channel. I can pull down and assign it a different DAC, I can assign it a different amplifier, a different speaker, and it essentially pulls that data into the spreadsheet so I can do quick comparisons. And that's one of the really helpful things when it comes to doing a design for me, is that I can figure out, will this speaker actually hit the target that I'm looking for at the distance I'm looking for, at the same time maximizing the noise floor. So I'm going to be going through this entire spreadsheet in this, and it's gonna get a little geekier as I go forward. I did want to mention that Benchmark Media, the amplifiers and DACs that I use, they have a spectacular calculating system on their website. If you go to benchmarkmedia.com and go to their calculators, they put in a whole bunch of data, and it's not just their amplifiers. They let you put in the numbers and see where your gain structure is going to end up, and see how much noise you're going to have out of the speakers, and even whether that's going to be audible from the listening seat. It's really fantastic. And I actually used it a lot when I was validating my math on my spreadsheet to make sure all the math was right. All right. Let's get into this. So the first thing we have to do is start at the beginning of the chain. We need to be able to get a useful unit that is comparable and works all the way. To be mad that I didn't use DBR, because that's a new CEDIA thing, but I did this way before DBR was coming.
We'll cover DBR
out.
fine.
So my system's in DBV. So a DBV is useful logarithmically. The reference is 1 volt RMS equals 0 DBV. A positive number are for voltages above 1 volt RMS, and a negative number are for voltages below 1 volt RMS. And if everything in the system is calculated in DBV units, or you can use DBR, simple addition and subtraction can be used. And whenever you're trying to do math with voltage, you don't really want to be doing just straight volts, because you get a lot of crazy leading zeros and millivolts, microvolts. It just gets really confusing. So DBV is a way to make everything be on the same common ground. And so as an example, if a preamp has 6 volt RMS, you can calculate the DBV value. These look intimidating as equations, but if you turn your iPhone sideways and put all the parentheses in, it's really not difficult to get this answer.
And for those that don't know, what would 6 volt RMS mean? What does it actually represent?
So 6 volt RMS, when you go do this equation that's on the sheet, it's 20 times log 10 of 6 volts over 1 volt, and that ends up being 15.5 dBV. So that's just what the output voltage is in dBV.
So 20 log 10 is a something we'd use in audio a lot, because it's the same calculation as we'd use for anechoic propagation loss from a speaker. So that is going to be an increase of 6 dB every time you double something. So 2 volts RMS would be 6. So this is where we were talking in amplifiers, where you double it, it's 3 dB of doubling. 20 log 10 means every time you double it, it increases by 6 dB.
Yeah, and you don't need to know really what log means, other than it's not a linear scale, and your calculators can do it for you. Nobody has log tables in big manuals that they look through anymore. Everybody uses a computer or their phone to do it. So you don't really have to understand how to do it manually to use this equation. And it's no harder than just putting in multiplication and division if you're putting it into a scientific calculator like an iPhone when you turn it sideways. So it is not a difficult thing to do. Okay. So we need to get we need to understand what the preamp noise floor at the rated output is. So a lot of times preamp manufacturers, well, they're not going to give you generally what the actual dB percentage, and the equation on the screen now is essentially to calculate the signal noise ratio. would put that into the equation where it says percent noise. So it would be 20 log 10 of 100 over 0.0001. And that would give you 120 dBV. So that, I'm not going to fix that. But with everything in dB, you can calculate the preamp noise floor. Oh, it was right. So you subtract the signal noise ratio. It is 120 dB signal output level that we previously found, and that gives you the residual noise floor. So, sorry, I got my brain a little confused. This is confusing for even electrical engineers. All right, so this is when I wanted to talk about the two different kinds of volume controls, digital and analog. We touched a bit also, we touched a bit already in this call. So there's also a hybrid approach, and but that makes predicting the actual noise floor difficult without lots of measurement data, and we're not going to get into that today. So even if you have an analog volume control, it may still have a digital readout. So just because it says, 30 dB, 32 dB, and you have it on a little digital readout on the front, that does not mean you have a digital volume control. So knowing what type you have for each gear is important. So most analog volume controls in our industry use a chip-based integrated circuit. There are, in the high-end world of hi-fi audio, there are other types of volume controls. Some use a resistor ladder network with relays to switch between. Some use simple potentiometers. Some use active gain circuits to reduce the output voltage. So there is typically an active output stage after any passive attenuation in most of these to maintain a consistent output impedance and be able to have a good output that can drive most amplifiers. So this spreadsheet is a tool for design and is only an estimate. So the math here assumes a perfect analog volume control stage that doesn't add any noise itself. This isn't true, and it can't be true, but we need more than a single signal noise ratio spec to calculate that. So this is a simplification, but it is still worthwhile. And almost everything in our world that uses an analog preamp uses a chip-based integrated circuit. So it's one big integrated circuit, and it has 16 volume controls built in. And it's done because of manufacturing necessity and to reduce costs. It is not the highest end way to do it. And in the two-channel world, it is something that's somewhat frowned upon. So, but you kind of have to do it because 16 or more channels get expensive really quick and also take up a ton of space. A relay controlled discrete ladder network really just wouldn't even fit in the case of our preamps and would cost a fortune. All right, so the next kind of preamp is a digital volume control preamp. And so if your volume control is done, it's done in the digital world. So any processors that use an output that's an audio over IP, like Dante or any of those things, they have a digital volume control, and control multiplying the digital signal values by numbers less than 1 inside the DSP, so that all the digital signal ends up. So and most of the time in DSPs, the math is done with greater 24-bit. Go into it, but there is a way to do floating point math that doesn't round the interim data until it's sent to the data. Functions to be done in a essentially log, and then at the towards the output, it has to convert that back to a 24-bit or whatever output stream that gets fed to the DAC, and then the DAC directly can feed the analog output stage. Generally, there's no analog volume control in the signal path, but that's a design choice, and it is possible to still put additional analog volume controls in the signal path. And because it's coming straight from the DAC, the noise they produce is constant at all volume levels. So when you change the volume control and you put your ear next to the tweeter, you won't hear anything different when you raise and lower the volume, assuming that there's silence coming into the system and you're not playing a signal that has noise. So, but when you add too much attenuation, it moves the signal into the noise floor of the DAC. And moving the signal down a single bit mathematically is approximately 6 dB of attenuation. But let's say if like you were trying to reduce reduce it by 24 dB, that and the signal is worse than the spec sheet says it is. So in that scenario, the DAC isn't using the 4 most significant bits, as they're all zeros. So that's just how it's a trade-off to get the DSP and the volume control to work in the digital domain. So it's very important to go with a digital volume control that you have to take speaker sensitivity, all those things into consideration. And yeah, I think that's all I have for this slide. All right, I'm not seeing any more questions, so I'll keep going. So the next thing we need to do is we need to, again, convert everything to the same unit in dBV to make the math simpler. So we use the power rating for the amplifier at the nominal speaker impedance, not just the 8 ohm rating. So you do need to make sure that you're actually doing the math on, in your case, for your speaker load. So let's say if we have a 4 ohm speaker and a 100 watt amplifier, you put those numbers into the equation on this sheet. So it's 20 log 10 over, the square root over 1. And that ends up as 26 dBV. It tells you what the voltage output in dBV is at the rated output. Calculate the amplifier noise floor in dBV. So most amplifiers are going to give you either signal to noise ratio as a percentage, possibly. And so you can use this equation just like we did for the preamp to get a percentage signal to noise ratio into into an actual dB level. So this equation will give you the residual noise floor in dBV with the input of the amplifier shorted, or essentially producing just its own self noise of the amplifier. And we subtract the signal noise ratio from the amplifier in dBV number of the amplifier noise. In this case, it was negative 72 dBV is what the noise of the amplifier is producing, just all when there's no signal. Now we need to calculate the combined noise floor. Unfortunately, because it's just not how it works, you can't just add the noises together because it's a system and the devices are connected in series. So we are making the assumption here, it's probably correct, that the noise from the preamp and the noise in the amplifier are not correlated to each other. So they are different noises. And so they both sound probably like shh kind of sound, but they're not at the same exact noise at the same exact time. So that's what makes them uncorrelated. And when you're adding things together in logarithmic dB math and the noises are uncorrelated, this is the formula for doing that. So when you add the amplifier noise and the preamp noise together in this example, you get negative 74 dBV is your total calculated noise floor of the amplifier preamp together. All right, and then I wanted to calculate the combined signal to noise ratio. So you subtract the noise floor from the rated amplifier output, and that gives us the combined signal to noise ratio. So even though our amplifier was the signal noise ratio of what it was stating as 104, the preamp in this particular example reduced that by 4 dB in combination. So you didn't actually get 104 dB signal noise ratio, you got 100. And if you do bad things in the gain structure, you can get a lot less than that. And so that's one of the reasons why we're trying to maximize this. All right. Next, we're going to calculate the preamp output level in dBV that will drive the amplifier to its rated output. So we found how quiet it should be. Now we need to figure out how loud can it be. And we need to get those to work at the same time. So this is when I wanted to talk about passive attenuation. So the passive attenuation between a preamp and amplifier, it works to reduce the overall system gain if the amplifier had a lower gain. And that is really, really helpful, as we mentioned, certainly in digital volume control systems where the noise floor is going to be constant. You essentially reduce the noise floor whenever you're the dB of the attenuation. An example in my system as we go to the end of how I did all the different pieces in my system. All right, so next we're looking at the headroom to from the preamp to get the amp to hit rated output. If this calculation is negative, the preamp doesn't have enough output voltage to drive the amplifier to its rated output. And in my spreadsheet, I highlight the cell in orange, a warning. So the reason you don't, it's a 200 watt amplifier, you don't want a preamp that runs out of juice earlier and is only able to get the amplifier to go to maybe 30 watts. You're essentially not even, you're going to hear distortion at 30 watts. You may think it's your amplifier, actually your preamp. So doing this calculation is, and in this spreadsheet if you have an analog volume control for signal to noise ratio, I transfer the number back to the spreadsheet so that the signal to noise ratio is in the condition where the preamp is able to drive the amplifier to its rated output. Essentially, I'm just trying to say that I'm trying to maximize the signal to noise ratio. You are in an analog volume control, you're just going to turn it down or turn it up so that the amplifier can hit it, assuming that you can, if your preamp can drive the amplifier, if it can drive 6 dB more than the amplifier needs, you have 6 dB of extra headroom. And in my calculation, I just subtract that 6 dB at the beginning, knowing that you're probably not going to be turning it up beyond where the amplifier is clipping. So anyway, sorry, I get real nerdy real quick.
And we love you for it.
I know, and I'm probably saying something wrong, and when I listen to this in the future, I'm going to be mad at myself, but it's okay. Next, we need to figure out how loud it will play. So we need to calculate the max SPL at 1 meter for the speakers. So this essentially is the equation to figure that out. So let's say for this example, we have a 6 ohm nominal impedance of the speaker, and it is 93 dB sensitive. So when you do the math, it ends up at 114.76, I think is what I have. No, it's 116. Sorry. I didn't have a chance to edit these sheets, but 116. So that's what it is capable of doing at 1 meter. So that doesn't solve the problem. So there's so many things that it can attenuate a speaker's SPL output compared to what it is measured at 1 meter in over air. Most of us are putting acoustically translucent projection screens at the best ones around 2 dB of loss. So you have to factor that in. If these speakers are behind any wall fabric, those can range anywhere from 1 to 12 to terrible, and they can vary greatly by frequency. So you want to be very careful about the wall fabric you use, but when you're doing the calculations, you need to account for it. Speaker toe in. A speaker at 30-degree angle can drop the SPL by 3 dBs or more. and because all speaker specifications are on axis. You also should think about the DSP equalization and target curves you're going to be using. So most automated EQ systems can add 6 dB at any gain, of gain at any frequency, and that needs to be calculated as a loss. So any bumps you want to put in the target curve to make your house curve the way you want it to be also need to be considered and are calculated as a loss here. In a actual room, you will get room gain. All of these calculations are anechoic, what it would be in a room that has no reflections, but room gain does help you out in actual rooms. What I will say is you're not allowed to use that as part of your calculation in RP22 calculations if you submit it for an award. And so those are all specified as anechoic calculations. So if you are using this spreadsheet to calculate RP22, you'd set the anticipated room gain to 0. But you also can set your DSP equalization to 0 as well, because in RP22 we're kind of assuming that you're the EQing the system to flat and the room gain kind of balance each other out. That's just the easiest way to design a system. All right, so now we need to try to find the noise floor at 1 meter. So the calculation in my spreadsheet takes the losses and room gain into account. So you take the maximum SPL that you just calculated and subtract the signal to noise ratio that you have calculated, and that gives you the noise floor again at 1 meter. Okay, so I did want to cover this just to talk about it, but we're not going to go into it deeply. So most speakers we deal with in our rooms are point sources, meaning that they radiate sound in a spherical pattern, and they dissipate in the sound they make dissipates throughout the room at a very specific rate, 6 dB every time you double the distance. Line source speakers are different. They are, however, incredibly rare. And in order for this equation to work, you actually have to have the speaker extend fully between the floor and the ceiling. And the floor and the ceiling have to be fully reflective in order for it to actually be a true full frequency line source. So very few circumstances where we would install speakers, even that say they have a line source capability, very few systems are actually installed in such a way. So line sources have the advantage. They send audio into a cylindrical waveform instead of a spherical one, which loses less audio over distance. But again, that is not something that most of our systems actually get to take advantage of. But I did, in my spreadsheet, I do say whether a speaker is line source or point source and uses math differently for those two. In reality, the line source speakers that we typically would use in a high-end home theater are somewhere between 3 dB and 6 dB loss for doubling distance, and that would vary by frequency. All right, so the next thing is noise floor at the listening position. Again, we're not at 1 meter, we're at the listening position. So ultimately, this is calculated with using the equations below, using point source or line source. If the number is below 0 dB SPL, it is technically below the threshold of human hearing for that speaker at that distance. If it is above 0 dB SPL, it could be audible in the right environment. So you are trying to get your noise floor to all be below 0 dB SPL, but that would be what it would, 0 dB SPL would mean that it would be audible at that distance in an anechoic chamber with absolutely no noise in the background. Obviously, that is not the rooms we are dealing with. So a little bit positive is not the end of the world, but obviously we are trying to minimize it. All right, the next big thing, and this is probably overemphasized in all the RP22, when people think about systems, probably the only calculation they would ever do is what is the max SPL you can get. So I calculated max SPL for each individual speaker, but I also want everybody to think about that. What is the total max SPL with multiple speakers? So this is an academic number. because it would mean that every speaker is playing an uncorrelated signal at the rated amplifier power. I do not want to be in the room when that's all happening. In real sources at real rooms, all the signal would likely be correlated, which would be using a different equation, and also, yeah, your amplifiers would probably not actually be able to do this all at the same time. It would be quite a high-end room that would be able to ever hit that number. So, then I wanted to calculate the total noise floor with multiple speakers as well. So one thing that you have a problem with when you have these high count systems, and 11 is still high, if you have a noisy amplifier or bad gain stage, you might not hear just one speaker when it's plugged into the amplifier with the gain stage you have it set up. But when you have 11, those multiple noise sources add together, and then together as a group, they may become audible. So the more speakers that are producing noise, the more likely that this will be a problem. So I use this equation to essentially calculate all the different noises from all the different sources in dB to figure out what the total noise floor would be at the listening position. And if you end up getting that number to be negative dB SPL, you will not be able to hear it. That's just the definition of that. I'm probably not going to go into this because this was probably way beyond the scope of our talk today. But the room HVAC also combines with the speaker noise. And essentially what we are trying to do here and today is to try to keep your speaker noise floor well below the noise floor of the room so that your speakers don't produce any additional sound when they're not playing something. But I basically built part of the spreadsheet to be able to calculate the SPL of the HVAC, added together the speaker noise to see how much it influenced it. And in this particular example, it didn't increase the dBs at all. So that was just a good indication. And then, yes, so that was it. So let me go back to the beginning of this. I want to talk a little bit about my room. It's a long presentation. I'm sorry for that. So this is my room. And I did some weird things because I'm a weird guy and I have a very particular viewpoint. I very much like the way that the Trinnov DACs sound. I think they do a spectacular job, but at 16 channels of DAC in one box, they just don't have the space, physical space in the box, or the amount of resources and money to build the highest end DAC in the world for 16 channels. So Trinnov on the Altitude 16 has digital outputs, and I use one of the digital outputs going to a benchmark DAC, which is one of the it's a DAC that comes close to what is the possible with the state of the art for DACs. And the other great thing about it is it has adjustable gain. So my left and right channels only are using an external DAC. And the external DAC and the amplifier, which is also a benchmark amplifier for those two speakers, both the DAC and the amplifier both have gain structure capable adjustments. They both have dip switches. So I was able to, using the math on these equations, figure out which of the gain settings needed to be done so that I could, so that the highest output of the DAC would essentially just take the amplifier to clipping and increase the signal noise ratio so that the noise that I'm producing in the room is as low as possible. And yeah, so in this room, I'm actually there is no way that I'm ever going to hear hiss at my seat, because the calculated output, the calculated noise at my seat through every single thing is negative 24 dB SPL. You would not be able to hear that even in the quietest of rooms. It's just beyond human hearing. And that's really what I wanted. You can't even hear it when you put your head up against the my center channel is slightly different. It uses the same amplifier, the same benchmark amplifier in monoblock mode, but I'm using the Trinnov DAC. And in that circumstance, I'm not getting quite as good of a signal noise ratio because again, the Trinov is excellent, but it is possible to do a little bit better, spending a lot more money and having a much bigger external box. So so it's just a compromise I was willing to make. And I did it because I wanted my left right in 2-channel mode to be as high end as I could possibly make it and have the lowest signal noise ratio, and also to use as many of the digital bits as is possible to make all that happen. Then the rest of my channels, I did not have the budget for a Trinov amplifier at the time. I could probably have done it now. I decided to go with an ATI amplifier, which uses similar modules, Class D modules, an excellent amplifier, but its gain is 28 dB, which would not have matched the Trinov. And so essentially, if I did not put 10 dB pads in between the amplifier and the Trinov, I would have had a 10 dB higher noise floor, and I wouldn't have heard my front 3 speakers, but I might have heard my left and right surrounds from my seating position. So I wanted to maximize that. Yeah, so that's essentially how I calculated the gain stage for this room. Yeah, so I think I'm kind of done with my soliloquy, and I guess it may be time to have discussions, and I can answer questions, and obviously Ben and Ryan are going to have lots to say.
Are we going to try to put our cameras back on, Ryan?
No.
No. You think this?
So
it was much better. It still fell out a little bit, but it was much
Sure.
better than it was at the beginning. I think, to reiterate what the point of this is, and I think Adam did there at the very end, is a gain structure that does not match appropriately. You are going to run into issues with something like a hiss when nothing is playing, and you are potentially going to run into clipping when you're pushing towards or at max volume. So you're going to lose dynamic range when you get into that upper echelons. I guess you're losing dynamic range potentially on both sides because the hissing could create loss.
Yeah, you've got the other problem, I guess, if you were to use an amplitude 16 with a normal consumer AVR. So you take like a Denon or Marantz and you decide to add some amps and you go with a Trinov Amp 16, you won't be able to drive it to its full power.
No,
because it needs 6 volts to drive it to full power. The consumer AVR is probably putting out 1.2 to 1.6, somewhere in that region, normally 1.4-ish. So you can't get all its power. So you've got these multiple problems of more power than you ever need, pushing things into clipping, creating hiss because you're multiplying noise, not reaching the full potential. Like there's loads of, if you don't get this right, it can go wrong in.
Not reaching your full potential is probably the least worst of all of these issues, but you're just wasting money at that point, I think, is the biggest part of that part of the equation.
Yes, but if your preamp is clipping, it sounds just as bad as if an amp is clipping.
That is true. Yes, that is true. You're clipping in a different place.
Yeah.
And you won't realize which thing is clipping. You might think it's your amplifier because everybody thinks, oh, my amp is clipping. Well, it could be your preamp.
Yeah. Yeah. So if you guys have questions, you can drop them into chat. If you don't have questions, that's great. We can call it. But this is a time, if anybody has questions in regards to gain structure or anything around those lines, to fire away. We can ask Adam about them.
One thing we should touch on before we go is that professional amplifiers that are designed for PA systems generally are not designed with noise floor as a particular concern. And they may be very powerful, but you're likely going to hear some hiss. And that's something that everybody just needs to take in consideration. They may be less expensive, but less expensive probably does not mean better in the sense of our style rooms, because we're not using them in a PA way.
No,
and
I guess that's important for subwoofers, right? Would you, if you were going to take a big Crown touring amp, how happy are you putting it onto a subwoofer versus a high sensitivity horn loaded LCR?
I think it depends on the sub. I mean, subs can have high sensitivity as well. I know in my particular situation, if I get right up next to some of my subs, I can hear hiss. So
I mean, I
it's
think the answer really is do the math. Even if it's
yeah.
for a
Right.
subwoofer, don't make the assumption that the amplifier is not going to that its noise is not going to be the problem. Do the math. Make sure that it isn't going to be the problem. Just do the calculations, assuming that the subwoofer is a full range speaker, which from how it sounds in a room, the amplifier is after the crossover point. So it is producing noise at all frequencies, and the subwoofer is probably less efficient at producing 20 kilohertz, but it can probably still play something if it's a passive sub at 1
Yeah.
kilohertz, and you still might hear it as a hiss.
Well,
Yep. I mean, I
maybe we don't have any
think
questions.
historically people have not considered or accepted that. I think there is it's easy when you are looking at subwoofers to think I need 2,000 watts or 4,000 watts, but not looking at the highest quality amplification. So suddenly you're buying those kind of products, the kind of things that are usually used in PA systems or live touring rigs. And if you're playing to a crowd of 1,000, you're not worried about a few dB of noise floor. But once you bring those in your room and stick it on 2, 4, 6, 8 subwoofers, well, you need to do the maths and find out if this is going to be a problem or not.
Yeah. And of course, doing the math will tell you, is the noise floor of my room going to cover up any potential issues that I may have with something like hiss, if that is what you're trying to overcome? And I do think you can get away with a little bit more on subwoofers. The human mind is a little more forgiving when you get lower in the frequency range, even with hiss or distortion or anything that we're getting at. But yeah, the easiest thing is head this off at the very beginning, do the math, try and not run into any of these problems, get them out of the way during the design stage of this. And that's something that a lot of enthusiasts don't do. It becomes, oh, look at this nice shiny thing. I'm going to go buy it because it's cool. When you really should be starting in the design stage, doing the math, figuring out what new shiny thing makes the most sense in your application, and then going from there. Don't forget
Yeah,
that
and
that first step.
one other point with doing the math is don't bridge or overpower a high sensitivity speaker unnecessarily. There is just no point to put a 2,000 watt amplifier on a high sensitivity horn loaded speaker because you just can't use it, and you're screwing up your noise floor and you get literally no gain, no benefit.
Yeah. Yeah.
Yeah,
So,
well, hey, we've just done that on a project, but many of the surround speakers did need to be bridged. The room's huge, so like the height speakers, front height speakers that are now behind acoustic transparent fabric or the screen, a long way away, they needed to be bridged. And potentially, when I was doing the numbers, I took the easiest route of we'll bridge all of them. Got in the room and it was like, I don't need that extra 6 dB of gain on all these speakers. But
or
the
that extra
closer
6
ones,
dB of noise.
I
from
do
that.
want to drop the noise. So
Yeah.
from how I first drew it to how we built it, actually we've only bridged the ones that actually need that power because they were going to become audible and we couldn't accept that. You know, we'd done everything to keep that room quiet. And it does now mean I have a mix of bridged channels versus not bridged across different surrounds, depending on their distance. The maths told me which ones I could and couldn't do it. We tested it, we proved it, we lowered the noise floor.
Yep. And not bridging a channel will actually still help the power supply of that amplifier be able to put more power where it needs to go. So even if you leave a channel unconnected, if it has a shared power supply, you've still done better for those other 3 channels, allowing it to do what it needs to do. But bridging an amplifier essentially is 2 amplifiers put together, and whatever their noise floor was, you double it. So it is not necessarily a good thing. And I did the calculations to figure out, did I want to bridge my amps or not? And I bridged the amps. If I was purely a hi-fi guy, never would need to bridge the amps. It gets way louder than I would ever need in a hi-fi scenario. But I did the bridging because I wanted to hit a very specific RP22 level target. It's definitely not level 4, but I wanted to hit that target, so I bridged the amps for that purpose. Also knowing that my noise floor was ridiculously low, so bridging it still meant that there was no way I would hear the hiss. So it's like all the math was done beforehand. So I knew what the likelihood was going to be. And then in practice, I made sure it worked. And that's exactly what you did, Ben. And you had more channels than you probably needed of amplification because you planned to be able to bridge them in case that was what in practice you needed to do.
Exactly.
But you knew that sometimes you would bridge them and sometimes you wouldn't. And the other thing that's weird is you may bridge the ones you don't even think about. Like it may be the left, center, and right. They may be higher sensitivity, but you may actually not need to bridge those. And you may need to bridge like a random surround because it happens to be further away and it's much less sensitive.
Right.
The which channels need which amount of power is something that you really need to work out with math and not just use a rule of thumb. It's like the front channels need the most power. Not if you're using a Black Swan necessarily.
Yeah, that's a really key point. And I think people do that a lot, whether it's by amping or by wiring or, bridging things, just automatically assume that the LCR need the most, which if they were all the same sensitivity speakers is a pretty valid thing. They often are further away from you than the surrounds, and they often are playing more content or louder. But if you're using different speakers and they're much more sensitive, it could be they really don't need much power. The horn on a Black Swan is rarely taking more than a couple of watts.
Mm-hmm.
It just doesn't need it.
And ceiling speakers that are inherently small because they just need to be to fit where they're going to fit are also likely much have a lower sensitivity. So they probably do need more power. And you may also find that you'll find a limitation somewhere. The speaker can only take, say, 200 watts, but they actually need 500 watts to hit your level. That's not the right speaker for you. Doing all these equations not only does your gain structure, but it also lets you design from the beginning whether the speakers will hit the targets that you're looking for to make a very balanced solution. And you have to consider all the things together in totality and not just shoot for max SPL or like any one of the individual parameters. All the parameters are important. And so you have to think about them all at the same time.
Oh, yes. And that's, it's an interesting thing, isn't it? This is how designing a system from scratch is different necessarily from upgrading and updating things. I wouldn't want to be changing anything in the system without going through these numbers. But if I'm designing from scratch, it's the basis. We wouldn't be making any decisions without understanding the implication. Okay, well, we pick that speaker, we'll need this much amp power, or the other way around. Okay, we can't have that much amp power because we can't get that much power out of the wall. If there's a limitation somewhere, work out which is the most compromised, what are the project constraints, and work around them.
Yep. And that could be a different answer for different rooms. The room that I'm sitting in now, I made specific design constraints because I wanted this to be hi-fi first. And it's still a really nice theater, but it is not. It probably maybe hits level 2 in some ways, but in other ways it only hits level 1. And that was known, but that was just what I'm doing here. In the building I'm building behind my house, I have to, for level 4, I have to start in a completely different mindset. And it's just not even going to be, it's not the same set of equations. Even though I'm the same person, I'm looking for a different thing in that space than I am in this space. So the variables are different for each room, for each purpose, for each end user.
Amen.
Anything else before we wrap this up? No? Okay. Well, we will wrap this up for now. I know we had some audio difficulties there. We can blame Restream or we can blame the internet. I don't think it was Adam's fault because he was working fine before. I think it was just the internet in general. If we need to, we can revisit and re-record, and I can upload things to YouTube outside of this.
Yeah,
but
if anybody has questions or specific numbers for us to look at, just put them in the normal chat, not the live stream chat, and then we'll see them and can answer them. We don't look at the live chat after it's live.
Yep. So if you guys have questions, just drop them in the VOD comments. Do not put them into the live chat. And we will get back to them as we can for Ben and I. Or if it's directed at Adam, we can have Adam answer the best that he can. So thanks for joining us, everybody. This was a discussion on gain structure with Adam Keplinger of Casaplex. And yeah, we will see you guys in the next one. Adam, thank you for joining us. I know I learned a lot through that process, and I hope people realize that gain structure is just as important as virtually everything else going on in the system, if not more so, in making sure that you can get the most out of your system. So, guys, we will be doing another home theater review, rooms in review on Thursday. Not sure what that room is. Ben and I try and stay away from them so you guys get an authentic reaction to what we think of the spaces when we're actually seeing them live. But we'll leave it there. Thanks for joining us, and we will see you guys in the next one. Thanks again.